In this section of the course, we'll take a look at the basic structure of a simple C++ program. First, we'll look at the basic components of a C++ program. These includes things like keywords, identifiers, operators, punctuation, comments, and syntax. Then we'll discuss the preprocessor directives that C++ uses. These are the statements that begin with the pound sign or the hashtag. And we'll discuss what they do and how they work. We'll then take a look at the main function specifically and functions in general. Then we'll discuss what C++ namespaces are and why we use the standard namespace so often. That's the STD word we've used throughout. We'll then learn about the types of comments that C++ supports and why we use comments in our code at all. Finally, we'll talk about basic stream input-output using cin and cout. Let's get started. In this section, we'll talk about keywords, identifiers, punctuation, operators, and syntax in programming languages. Most languages have keywords. Keywords are part of the vocabulary of a programming language. In most languages, the keywords are also reserved. This means that you, the programmer, cannot redefine their meaning, and you can't use them in a way in which they were not intended. C++ has lots of keywords. In a browser, I've opened up a web page for cppreference.com that lists the C++ keywords. Without a frame of reference, it's difficult to know that this is a lot of keywords. There are around 90 keywords in C++. Java has around 50. C has 32, and Python has 33. 90 is a lot of keywords. Now, in general, the more keywords that a language has, the more complex the programming language grammar. However, there are many keywords in C++ that are rarely used. I've been using C++ for a very long time, and there are some keywords in this list that I've never used. There's no need to sit down and memorize all these keywords. We'll use the keywords as we need them, and you'll learn them along the way. Notice that some of the keywords in this list we've already used. For example, we've used int and we've used return. Here's int right here, and here's return right here. We used that in our first program. Also notice that pound include, main, favorite number, standard, endline, cin, and cout are not in this list. That's because they're not keywords. We'll talk about them next. What's important to remember here is that C++ has a set of keywords that it's defined in the language, and these words are reserved. Now let's go to CodeLight and see the reserved words in our first program. So now I'm back in CodeLight, and I'm looking at the same program that we did in the previous section, the one with the favorite number. You can see that I mentioned that main and pound include and favorite number and so forth were not keywords. Same with standard out, cout, cin, and so forth, and endline, all of these. These are not keywords. These are called identifiers. And there's an important distinction between identifiers and keywords. An identifier is something that the programmer names. So these names have been created by programmers to create something that represents something meaningful to them. There are rules about how to name identifiers, and we'll go into all those in a later section. C++ also has operators. It's got a lot of operators. It's got the operators that you're used to, your addition, multiplication, subtraction, division, and so forth. But in this case, we're using some non-standard operators. For example, this guy right here, that little chevron, is the stream insertion operator. We're going to insert whatever's on the right-hand side of it into that stream. In this case, it's an output stream that gets displayed to the console. Same thing with the string extraction operator. This one takes something from the console and stores it into a variable, in this case, favorite number. There's also that double colon right here. That's the scope resolution operator. We'll talk about all of these operators as we go on to section 9 in the course. C++ also has punctuation. Things like semicolons at the end of statements, curlies, open and close quotes, parentheses. It's got all kinds of punctuation. When you put all of these elements together in a program, you end up with something called syntax. Syntax is the syntax of the programming language, the structure and the meaning of what you want the compiler to understand. The compiler is taking your code and translating it to machine code, and it's translating it based on what you told it you wanted to be done. It's not going to guess. This may sound a little intimidating at this point, but it comes pretty quickly with a little bit of practice. Well, that completes this video. In the next video, we'll talk about the C++ preprocessor, and we'll learn more about that preprocessor directive, pound include. In this video, we'll briefly go over the C++ preprocessor and preprocessor directives. What is the C++ preprocessor? The C++ preprocessor is a program that processes your source code before the compiler sees it. The C++ preprocessor first strips all the comments from the source file and replaces each comment with a single space. Then it looks for preprocessor directives and executes them. Preprocessor directives are lines in the source code that begin with a pound or hashtag symbol. As you can see in this slide, there are quite a few preprocessor directives available. The most commonly used preprocessor directive is the include directive. When the preprocessor sees this directive, it replaces the pound include line with the file that it's referring to. Then it recursively processes that file as well. So, by the time the compiler sees the source code, all comments are stripped out and all preprocessor directives have been processed and removed. Preprocessor directives are commonly used to conditionally compile code. For example, suppose you only want to compile a portion of your source code if you're on the Windows operating system. In this case, you would use a preprocessor directive to test to see if you are on Windows, and then perhaps include some Windows-specific libraries. If you're not on Windows, then maybe you want to include some Mac OS X libraries, or use the error directive to abort the compile with an error message. Conditional compilation is beyond the scope of this course, but we'll use several preprocessor directives as we move on in the course. One final note that's very important to understand. The C++ preprocessor does not understand C++. Let me say that again. The C++ preprocessor does not understand C++. It simply follows the preprocessor directives and gets the source code ready for the compiler. The compiler is the program that does understand C++. Okay, that wraps up this video. In the next video, we'll talk about comments in C++. In this video, we're going to talk about comments in source code. Now, comments apply to just about every programming language out there. C++ has two kinds of comments, but before we talk about those comments, let's talk about what comments are in general. Comments are programmer-readable explanations in the source code. Explanations, notes, annotations, anything that adds meaning to what the program is doing. One thing that's very important to understand is that the comments never make it to the compiler. In C++, the preprocessor strips out the comments so that the compiler never sees them. It may sound kind of weird, right? We're writing something that the compiler is never going to see. That's the whole point. This is human readable. This is for the next programmer that's coming down the pipe, or for yourself when you have to go back and modify code. You can leave comments in the code explaining what you did and why you did. C++ has two styles of comments. The first one is just a single line comment, and I'll show you what that looks like. It's basically two forward slashes side by side, and then everything after that until the end of the line will be ignored. So this is a comment, and the compiler will never see that comment. That's only for your eyes only, or for the eyes of programmers coming after you. So that's a single line comment. Typically you see these comments done like this, or you may see them, for example, here, right after this variable declaration here for favorite number. We could do something like // this is where my favorite number is stored, or something like that. That's kind of a silly comment, and I'll talk more about using these things wisely. The compiler is never going to see this because the preprocessor will see the comment and strip it out and just replace it with a single space. Okay, so that's one style of comment. That's a single line comment. The other kind of comment is a multi-line comment, and that's a slash, again a forward slash followed by an asterisk, and then an asterisk followed by a forward slash. So everything between those two elements is a comment and will be ignored. So this could be, this one spreads across lines. So this could be a multiple line comment like that. You do anything you like. And again, it's totally free form. You can make it look however you want. You can indent, you could do anything you want here. Everything in here will be ignored. Okay, so now let's talk a little bit more about these comments and what makes sense, what doesn't make sense. The idea behind programming is literate programming. Basically, your code should be self-documenting. Does that mean we don't write comments? Well, no. So you want to be sure that what you write makes sense. In this case, here's my code. Here's my main, and that's the block of code that I've written. This is pretty self-explanatory. I mean, I'll leave this comment in here. I'll fix that typo here. But there's an integer called favorite number. You're outputting to the console, enter a number, you're reading from the console, and you're printing out some stuff. This code doesn't need any commenting. It's very, very clear what it's doing. That's not always the case. Sometimes code is very complicated. It's using some complex algorithms. Maybe you're using some really clever efficiency tweak to make it run faster, but it makes it less obvious what it's doing. Those are good examples of where you should use comments. Don't comment the obvious. For example, right here, you don't want to say return 0. That's silly. I mean, I know I want to return 0. I just said it in the code. So those kinds of comments you really don't want to use. Also, if you're adding A and B, you don't want to put a comment that says, adding A and B. It's pretty obvious from A plus B what you're doing. So you really want to explain more complicated code. You also want to keep the style of the comments consistent. So for example, I have this line comment here, which goes toward the end of the line. Over here, I really don't want to do the other style comment and do something like that. You want to keep your style consistent. Now, the multi-line comments are often seen at the top of files. So I'll do this, and in this case, CodeLight kind of helps me out a little bit, but I'll do that. So many times you'll see code that looks like this. You'll see a bunch of asterisks on top, and then you'll see a bunch of asterisks down here, creating like a little header block. Now notice I've got a beginning comment here and the end of the comment here. Everything in here will be ignored, but in here you'll see stuff like author, and I'll say Frank, dates, things like that. Copyrights, license information, a lot of that is very commonly seen in a multi-line comment at the top of the source file. Another good example of a good comment would be, suppose that inside this function, I'm doing some kind of algorithm and I've tweaked the algorithm. So I could do something like using a modified version of Dijkstra's algorithm, let's say. To improve space efficiency or anything. Something like that. Now, the programmer coming after you understands that you're using Dijkstra's algorithm and you've modified it somewhat. Dijkstra's algorithm is a very well understood algorithm. So you've tweaked it somehow to improve space efficiency. Maybe in the body of that algorithm, you can comment what exactly you've done. Okay, so that's an example of a good comment. So again, don't comment the obvious. Good commenting doesn't justify bad code, obviously. You don't want to write really bad code and then put a good comment in there saying something silly. One of the dangers with comments is that many times programmers use comments as version control. So up here you'll see something like, let's say 11/11/2017, and you'll see something like Frank fixed bug in something. And then another program will come across and they'll say 11/13/2017, maybe it's Joe, and Joe added function to do something. That's not a good idea. If you want to use versioning, use version control. Use something like Subversion or Git. Don't write your versioning here. The problem with this is some programmers will do it, some programmers won't, and this really won't be reflective of all the changes that actually occurred in the file. Okay, so again, don't do this. This is not a good idea. Use a real version control system. Finally, if you go back and modify code, make sure you look at the comments and modify the comments if necessary. There's nothing worse than a programmer looking at some code and seeing a comment that looks like this, and then you look at the code and it doesn't look anything like Dijkstra's algorithm because another programmer changed it to something else and didn't change the comment. So it's real important that you keep your comments and your code in sync as you go along. Okay, that's pretty much it for comments. In the next video, we'll talk about the main function itself and talk a little bit about what's going on there. In this video, we'll briefly go over the C++ main function. Every C++ program must have exactly one main function somewhere. A C++ program can consist of hundreds of files, but one of those files must contain the main function. Note that the name main must be written in lowercase letters. When a C++ program executes, the main function is called by the operating system, and the code between the curly braces executes. When execution hits the return statement, the program returns the integer value to the operating system. If the return value is 0, then the program terminated successfully. If the return value is not 0, then the operating system can check the value returned and determine what went wrong. There are two versions of main, and they're both valid as per the C++ specification. So far, we've only seen the version on the left, which returns an integer and has nothing between the two parentheses. This version of main expects no information from the operating system in order to run. This is the version that we'll use mostly in this course. The second version of main is the one on the right. In this version, main expects information from the operating system. So suppose that when you execute the program, you need to pass information into the program from the command line. This is very, very common for command line applications. In this case, we tell the compiler that we need two pieces of information. First, we need the number of pieces of information that were passed in. That's argc. We can use any variable name here, but historically we use argc, which stands for argument count. The second piece of information is the actual arguments that we passed into the program. This is captured by argv, which is the argument vector. The syntax for argv looks a little strange, but it'll make sense as the course progresses. It's basically a bunch of strings, such as program.exe, argument1, and argument2 in this example. We'll talk more about strings and vectors as we move forward, but I wanted to show you both versions of the main function in case you're looking at code out there and you see the second version. Both are perfectly valid and both are commonly seen. Note that main must always return an integer. Main happens to be an example of a function. A function is basically a name that we can use to reference a block of code. In this example, main is everything between the curly braces. Functions are very commonly used, and we'll write our own functions as the course progresses. There'll be an entire section of the course devoted to functions. But main is a very special function. As we learn C++, our entire program will be contained inside the main function. And as our programs become more complex, we'll write our own functions and then classes to better modularize and organize our code. In the next video, we'll talk about namespaces and see how we can use them in our first program. In this video, we'll briefly go over using C++ namespaces. C++ namespaces can be a little confusing when you first see them. As our C++ programs become more and more complex, our programs become a combination of our own code, the C++ standard libraries and their code, and libraries from third-party developers and their code. So as you can imagine, sooner or later, we're going to run into the situation where Company X names something the same as Company Y. When we use that name in our program, the C++ compiler doesn't know which one to use, so we have something called the naming conflict. For example, suppose another library that we're using has defined a name called cout. Well, that's a big problem, right? Because now C++ doesn't know which cout to use. C++ allows developers to use namespaces as containers to group their code entities into a namespace scope. That means that I could create a namespace called Frank, and I could define cout within that namespace. Now, if a programmer wanted to use my version of cout, all they had to do is say Frank : cout. That's it. If they wanted to use the one in the standard library, they would just say standard : cout. It's as simple as that. Namespaces are used to reduce the possibility of naming conflicts. The : operator is called the scope resolution operator. It's used to resolve which name we want to use. However, many programmers find it tedious to type std : all the time when using cin, cout, endline, and so forth. So C++ provides a few mechanisms to help in that regard. In this sample code, you can see that we're explicitly telling the compiler to use cin, cout, and endline from the C++ standard namespace using std followed by the scope resolution operator. This is how we've written all our code to this point. Now let's take a look at another way we can do this without so much typing. In this case, we can use the using namespace directive followed by the name of the namespace we wish to use. In this case, the standard namespace. Notice that I no longer have to use std followed by the scope resolution operator when I refer to cin, cout, and endline. The compiler now knows which one to use based on the using namespace directive. This is pretty easy to use, and it's the way I'll do it in this course from this point forward, since it reduces code clutter and it's better from a teaching perspective. However, this may not be the best solution for large programs. Using namespace standard not only brings in cin, cout, and endline, it brings in a bunch of other names that are defined in that namespace. So the possibility exists that you may still have a naming conflict. C++ provides another variant of the using namespace directive. Let's take a look at that. In this case, we have a qualified using namespace variant in which we tell the compiler exactly the names I want to use from a specific namespace. In this case, you can see I'm using 3 using directives, each qualified for a specific name in a specific namespace. The advantage of this approach is that we can still use cin, cout, and endline in our code without the namespace and scope resolution operator. And we're not getting any other names from the C++ standard namespace. For the examples in this course, you can use the namespace standard directive from the previous slides with no problem, but keep in mind that it may not be the best practice in larger programs. That wraps up namespaces. In the next video, we'll take a quick look at basic I/O with cin and cout. In this video, we'll look at basic input-output using cin and cout. Cout, cin, carr, and clog are defined in the C++ standard. To use them, you must include I/O stream. C++ uses a stream abstraction to handle I/O on devices like the console and keyboard. Cout is an output stream that defaults to the console or the screen. Carr and clog are also output streams that default to standard error and standard log respectively. And finally, cin is an input stream that defaults to the keyboard. The insertion operator is used with output streams, and the extraction operator is used with input streams. Let's look at how we can use cout and the insertion operator. The insertion operator inserts the value of the operand to its right, in this case the variable data, into the cout output stream. Since cout is by default the console, the value of data will be displayed on the screen. Since we're using stream abstraction, we can chain multiple insertions in the same statement. This makes basic I/O very, very easy to do. It's important to understand that the insertion operator does not automatically add line breaks to move to the next line on the console. You must do this explicitly, either by using the endline manipulator or by including a new line character, the /n you see in the last example. If you use the endline stream manipulator, it will also flush the stream. This is important to know since if the stream is buffered, it may not get written to the console until it's flushed. We'll talk more about this when we talk about file streams since it's more applicable there. Let's see how the extraction operator works with cin. The extraction operator extracts information from the cin input stream, which defaults to the keyboard, and stores the information into the variable to the right of the extraction operator. The way in which the information is interpreted is based on the type of the variable. So in this case, if data is an integer, then an integer representation will be read from the keyboard. If data is a double, then a real number will be read and stored. If data is a string, a sequence of characters will be read and stored. Extraction operators can also be chained. In the second example, 2 variables, data1 and data2, will be assigned values read from the keyboard based on their type. The characters entered using the keyboard will only be processed when the enter key is pressed. Cin extraction uses white space, that is, spaces, tabs, new lines, as terminating the value being extracted. That's important to understand, so if you put spaces between the things that you type in, the spaces will be ignored. It's possible that the extraction operator could fail. For example, suppose you want to read an integer and the user enters my name Frank. In this case, the operation fails and the data will have an undetermined value.
cin extraction is very easy and useful. However, we'll later learn about other methods we can use with cin that give us more control over the data that's being input. Finally, we can use the same operators to insert and extract data from file streams. This is pretty cool since the syntax is already familiar and the behavior is very similar. We'll work with files later in this course. Now let's head over to the CodeLight IDE and go over some examples in live code. Okay, so now I'm back in the CodeLight IDE, and I've got a Section 5 workspace. Within the workspace, I've created a basic I/O project, and this is the main file for that project. Now what we're going to do is we're going to do some basic I/O using cin and cout, and I'll show you some of the nuances so that you really understand what's going on here. First of all, remember on line 4, we've got to include I/O stream, and on line 6, I'm using namespace standard just to make the code a little bit easier to read. Best practice would be to actually include standard scope resolution operator cout and so forth, as we talked about in the last lecture. So, first thing we'll talk about is this statement on line 10 right here. Cout, insertion operator, a string hello world, we got another insertion operator, and then we've got the end line manipulator. What this does is it prints hello world to the console and then advances the cursor to the next line. Okay, I'm going to run this, and I'm going to run it by pressing Control F5, which is the same as run here. So when we build and run, you can see it prints out to the screen, hello world, and then it goes to the next line, and this time-elapse message prints out after that. Okay, pretty straightforward. If I leave out the end line, and I'll do that really quickly, and I'll run it again, you could see that it prints out hello world. It does not advance to the next line, and then everything just prints out right after that. Okay, so that's pretty straightforward. Let's take a look at a couple of other examples. Look at this example here. I'm going to uncomment this out. First, I'm displaying hello, and then I'm displaying world, and then I'm displaying an end line at the end. Notice that there is no end line after the first hello. So you would expect that these two should run together with no spaces. So we should see hello world all bunched together. So let's try that. And you can see that that's exactly what happens. You can see hello here followed by world with no spaces. It does advance to the end to the next line because we have that end line manipulator here. Okay, so let's do a few more. And as you can see by default, right here when we use the insertion operator with a string, in this case hello, it does not advance to the next line unless we do it specifically and explicitly. So that's what end line does. So here are 4 more output statements. The first one just says cout hello world, just like we've done before, and advances a line. The next one changed the insertion operators. So you could see that I'm putting hello on the output stream, then I'm putting world on the output stream, and you can see there's a space right before that W there, and then I'm printing a new line. So we're getting the same effect as the previous one. Same here. I could say hello world, but here in this case, you can see that I'm using a /n, a \n. This character right here is a new line character. So what happens is you can embed that new line character in the string, and it will advance to the next line. So it's similar to end line. It doesn't flush the buffer, but it still advances to the next line. And then the last line you can see that there's a couple things going on here. You can see that I've got a new line here, a new line here, and a new line here. So you expect this to print out hello, and then go to the new line, and then print out here, then go to the advance to the next line and print out there, and then advance to the next line here. So that's what we expect. We expect the first 3 statements on lines 15 through 17 to print out exactly the same thing. That's the same effect. And the last one to be a little bit different. So let's try this out. And we'll compile and run here. And you can see hello world, hello world, hello world, exactly the same. And then we have hello out there, 1 word per line. And remember, even though that this is all in one string literal here, we still have the /n's in there, which that's how they work. You embed them inside those strings. Okay, so now let's do a little bit with variables. We'll talk a lot about variables in the next section, but I'm going to declare 3 variables right here. And I'll explain that to you real quick. They're really easy. In this case, I'm declaring 3 variables, num1, num2, and num3. Those are the names. Num1 is an integer, and num2 is an integer. And then num3 is a double. That's a floating point number, like 2.5 or 100.7, a real number. We'll use num2 and num3 a little bit later, but right now we're only going to use num1. So I'm going to comment this line, uncomment this line, and you can see what's happening here. I'm saying I'm prompting the user, enter an integer. Then I'm reading an integer using the extraction operator. I'm extracting an integer from the input stream, and I'm storing it in num1. You can see it's going right in here. And then I'm simply going to output, you entered whatever they typed in. So let me explain how this works. Here's your keyboard. And remember, CN is by default tied to your keyboard. We can redirect it as we wish, but by default, it's the keyboard. Now what happens is characters are read from your keyboard, and they're not read directly by CN. They're stored in a buffer. This is done to make the program more efficient. So if I type in 123 on the keyboard, then what happens is the numbers are read from the buffer. The characters in this case are read from the buffer, and the compiler knows that num1 is an integer. So it's going to read those characters, and it's only going to process what makes sense to be an integer. So in this case, it's going to read the 1 and say, yep. It's going to read the 2. Yep. It's going to read the 3. Yep. Now we're done. So we've got 123. So 123 gets stored into num1, and that will print out here. Okay. Now you need to press enter when you do this on the keyboard. And also, white space is ignored. So if I type in like 10 spaces or tabs or anything that's considered white space, and then I type in 123, then I type in a whole bunch more white space, it'll all be ignored. Okay, so let's take a look at that in action. And I'll just clear this real quick. And let's run this. And it's going to say enter an integer. So I'm going to type in 123, press enter. Remember, I have to press enter. And it says you entered 123. Just what we'd expect. I'll run it one more time. And this time I'm going to type in a bunch of spaces. I'm pressing the space bar. Now I'm pressing tab. Then I'll press 123. And I'll type in some more spaces. Now when I press enter, you can see you still entered 123. All that beginning white space is ignored. And everything after the 3 is considered not an integer. So this is where if you read from CIN again, it's going to start right after that 3. Okay? So that gives you an idea of what's going on there. And let me comment that out again, and we'll keep going through some more examples. In this case, we're going to read 2 numbers. We're going to say enter a first integer, and we're going to read that into num1. Enter a second integer, and we're going to read that into num2. And then we're just simply going to say you entered num1 and num2. Remember, in this case here, num1 and num2 right here will be replaced by whatever values the user typed in. Okay, so let's do this. Let's run this one, and you'll see it's exactly what you would expect. And let's see. Oops, I shouldn't have commented these guys out. Let me uncomment them, and let's try that again. So enter a first integer. Let's say we want to type in 100. And I'm going to press enter. Enter a second integer, 200. I'll press enter again. You entered 100 and 200. Again, just what we expected. Now let me show you something that you might not expect. Let me run this one more time. And I'm going to enter 100, followed by a space, followed by 200. And press enter. You can see my output statement worked. It says you entered 100 and 200, but the output looks a little different, right? Well, you can see what's happening. I've entered 2 integers. So what happens is when I read those integers from the standard input, right, via the extraction operator, it's going to grab both of them. It's not going to wait because it's got both of them in there already. So it's not going to wait for me to press enter 2 times because it's got them in there. Let me show you what that looks like so you can better understand it. All right, so let's say that we're here. And we just ran this program and we entered 100, followed by a space, and I'll just use that character there for a space, followed by 200. Okay, so right here, it's waiting for me. What I did was I entered 100 space 200 and I pressed enter. The extraction operator realizes that num1 is an integer, so it's going to try to read an integer from this stream here. It's going to start right here and it's going to say, I got a 1, a 0, and a 0. Boom, I hit a white space. That must mean that my integer is done. So it's going to take 100 and store it right into num1. Now it's going to output enter another integer. And it's going to try to read that second integer from the input stream. Well, it's already in there, right? So it's going to start right here and it's going to say 200, hit the end. Aha, that's 200. It's not going to wait for me to press enter because there's already data in that buffer. So in this case, the 200 gets put into num2 and this will print out 100 and 200. So your output will be correct, but the way that the prompts are displayed is a little different because it's got data in that buffer already. Same thing with, let me run this one more time and I'll show you a little bit of a different example. Same thing with space 100 space tab 200 or 200, yeah. And you can see you entered 100 and 200. It's just ignoring all that space. But it's got those two values in that stream. It's just going to process the stream. It doesn't wait for you to press enter twice. Okay, so I'll comment those out and we can chain the extraction operator just like we can chain the insertion operator. So in this case, you can see that we've got the cin followed by an extraction operator right there, followed by another extraction operator, right? So what I'm doing here is the output statement for the user is a little different. It just says enter two integers separated with a space. So let's say I enter 100, a space, and then 200. Now this guy is going to read two integers from the input stream, and it'll assign 100 here and 200 here. Okay, let's do that. And you can see right here, enter two integers separated with a space. Remember, I could put leading spaces too if I want, but in this case, I'll just say 100 space 200. And it says here, you entered 100 and 200. This is actually a really handy way to get information from the user. When you want them to enter more than one number, enter three numbers separated by spaces. That's really easy for them to do rather than say, enter number 1, enter number 2, enter number 3, and so forth. Okay, so that's another option you've got. Okay, so I'll comment this out, and now we'll process some doubles. In this case, if you remember, let me scroll up just a little bit. If you remember, num3 was a double, right? So it's a floating point number, a real number. And what I'll do here is I'll just uncomment this out. And the prompt to the user is enter a double right here. And you're going to read the double into num3 from the input stream. Again, here's the input stream. Suppose I typed in 12.5. That's a real number. It realizes that it needs to read a real number from the input stream because num3 was defined up top as a double. So it's going to come here. It's going to read a 1. It's going to get the 2. It's going to see the decimal point. That's valid in a real number. Then it's going to read the 5. Then it's done. And 12.5 will be assigned here and will be displayed down here. Okay, so let's run that. Enter my double. I'll press 12.5 and enter. And it says right there, you entered 12.5, just like we expected. Okay, so let's do this last one, and I'll show you what could go wrong here. There's always something that could go wrong, right? So let me uncomment that. And look at this example here. This one is saying, enter an integer, and you're going to read the integer into num1. And then it's saying, enter a double, and you're going to read the double into num3. Okay, now if we run this and I type in, let's say 10 and 12 space 12.5, that's not a problem at all, right? Because it's going to read the integer and it's going to say 1, 0. I see a space, I'm done. The 10 goes into num1. Then it's going to read a double here, num3. It's going to say 1, 2, decimal point 5, 12.5. Perfect. It's going to go in here. The integer is 10. The double is 12.5, and that'll work just fine. Let me run that just so you can see that. And then we'll do one more example, a couple more examples where you can see some of the issues here. So there's my integer. Let's say it's 10, and the double is 12.5. And you can see the integer is 10, and the double is 12.5. Okay, but what happens if I enter something like, let's say 10.5? something like that. Think about this. Logically, you're probably guessing what's going to happen. It's going to read an integer. So it's going to see the 1 and the 0, and it's going to say, yep, that's an integer. When it sees the decimal point, it knows it can't be an integer anymore. So it's just going to take the 10 and store it here. Then you're going to say, read me a double. Well, it's going to start at the decimal point, and it's going to read 0.5. 0.5 is a double, right? So it's going to store 0.5 here. So your output is going to be 10 and 0.5. Maybe not what you expected, but you can see the behavior makes perfect sense. You're telling it what to do. You typed in 10.5. Well, 10's an integer and 0.5 is a double, and I can read those. So let's try that with 10.5, and we'll see what that looks like. So let's enter the integer 10.5. Now remember, there's going to be that 0.5 left in the buffer, so it's not going to ask me. It's going to ask me to enter the double, but it's not going to wait for me to press enter because it's already got data in the buffer. So I press enter, and you can see enter a double, right? It's not waiting for me here. The integer is 10, and the double is 0.5. Now the last example is, let's run this one more time, and we'll do something really weird here. We'll just type Frank. Now that's really wonky because you've just told it that you're going to read an integer and a double, and you just gave it a string of characters here. So if I press enter, you can see what's going on here. The integer is 0, and the double is some undefined, crazy small number here. Okay. Well, what happens is when it tried to read the integer, it got the F in Frank, and it's lost. So the input failed, and it goes into a fail state. From that point on, everything that's happening is unreliable. You can see that the integer got 0. It got basically initialized to 0 there. But everything else after that point is completely unreliable. You've got to be really careful. Now, in real world programs, we're not really using cin to read characters. We're using strings. We're reading them into strings, and then we're trying to convert those strings to numbers or whatever else we really need. But they're really, really handy and easy to use, and that's what we're going to do for the vast majority of this course. We're going to use cin and cout so that we can read numbers and we can output numbers or strings or whatever we like. So that finishes off this video. This is basic I/O using cin and cout. You can see it's pretty straightforward. Don't worry about mistakes right now as we're working through these programs. If it says enter an integer, enter the integer. If it says enter a string, enter the string. Don't worry about error handling. That comes later.